other than what some of you have come in and asked about already. But I've got this one up on the board, and so just to walk through that real quick. Right, this is a product rule, so this was one of them, a number 9. So it should look like this: derivative of x squared is 2x. Product rule, so you have to do the derivative of the first, would be -1 with the y left alone. Plus, remember, product rule always has a plus in it. Negative x left alone, and then the derivative of y is y prime. Plus y squared, derivative would be 2y times the y prime equals 0. I saw a lot of people putting x primes in, and we talked about that. You don't need x primes in here when you're doing the derivative with respect to x. X prime is just 1. You do the derivative with respect to x, the derivative of x is just 1. So when we do this derivative of negative x, we want to put -1 in it. We don't want to have an x prime in it. That just needlessly makes it more confusing. Yes?
Is it okay if we just leave it as a negative?
Yeah, oh yeah, you don't need the 1, but I'm just making that point. Yeah, you, just like the plus minus you don't need. Now, the other part of this is we want to get the y prime terms together. So we leave these on this side. I know I'm recording, and this is not going on the recording, but we'll get the rest of it on there. And so we got that, and then we take out the y prime. So this was the basic idea of this yesterday. And then finally we divide by that quantity. What's that? Did I mess something up? Right here. That should be +1. Right there. Yeah. Yeah, that's right. Okay? And so we end up with y prime equals that. Now, it might look different in the back. They might have taken out a negative on the top and bottom. And that's okay, though. You can just leave this here. See, and the reason for that is if I would have grouped the y primes over here, or excuse me, the y primes over here instead, then everything would have been opposite. You know, it's kind of like if you solve an equation, you have x's on both sides. If you get the x's on this side, it looks one way, and if you get the x on this side, they're all opposite. The answer comes out the same in the end. So I could pull a negative out of the top and get 2x minus y. And I could pull a negative out of the bottom and get x minus 2y. And then negative divided by negative would cancel out. Okay? And so I could have had that as my answer too. And that's probably what, that might be what the end of the back. Okay? Then you were supposed to tell which of those functions was which, and so you were supposed to plug like a 0 and a 1 in or something for x and y, kind of see what your slope was. The other one I wanted to talk about was 21. I had some people in this morning, and we talked about this one. And I was glad to see as I walked around the room, a lot of you had a lot of work on 21 and 22, and those, and you should have. I mean, there should have been something. Now, you could have shortcut your work a little bit on 21. On 21, they had, what was it? It was 2x squared plus y squared, and then equals 25xy. So when you go to do this one, I just want to go through the first step here with you. So when you go through and do this one, and what they were looking for here was the equation of the tangent line. So all we need is a point and a slope. Now they gave us the point. They told us the point was 1, 2. And now all we need is a slope. Well, that's going to be the y prime. Okay? And so we got to find our y prime. So we go ahead and do this derivative. We bring the 2 down here. We leave the inside alone. And then we times by the derivative of the inside. Well, the derivative of the inside is 2x, 2y, y prime. And then on this side, we're going to have to do a product rule. So I would keep the 25 with the x and then have the y there as the u and the v. So now my product rule, the derivative of 25x is 25. We leave the y alone, plus 25x left alone, times the derivative of y, which is y prime. Now that's kind of a mess. Now we want to get our y primes together. Well, the only way to get the y primes together is to FOIL this all out, right? And if this was the gateway test, if this was a problem on the gateway test, and this is probably beyond, this would be a quite nasty. And this would probably not be on the gateway test just because of all the algebra that's in it. I want you to do some algebra, but that's a little crazy. I'm thinking more like this for the gateway test, okay, on implicit differentiation. So you would have to distribute the 4 through there, and then you have to FOIL this, and you'd end up with like 4 terms over here. And a couple of them would have y primes in them. And then you got a y prime over here. So you'd get the 3 y primes on one side, the others that don't have y prime on the other. And then you'd factor out your y prime and do everything we did over there. However, on this one, you don't have to do that. Because all you need is your slope, so you can write the equation of your tangent line. So right now, you could put a 1 in for this x, you could put a 2 in for this y, and do that all the way along here, right? And then just solve for y prime. So anytime they're giving you numbers to plug in to find y prime, you don't have to get the y prime by itself. But if it was a gateway test, you would. If it was a gateway test, you'd have to go through and FOIL that all out and get it, and it'd be a big kind of algebra mess, but it's not bad. I mean, I did it this morning for some people that came in. And we looked at it. But it ends up coming up to be 2/11, I believe. I believe that's what the slope ends up being. And so then all you have to do is go y equals 2/11 x minus 1 plus 2. And so you're done. All right? Now they wrote it differently in the back. I mean, I'm not sure why they wrote it the way they did, but there's a lot of different ways you could work this at this point. We said we just leave it. When you do the equation of a tangent line, just leave it. Point and slope. They gave you the point, you needed the slope, you did that by getting the y prime. Okay? All right, so that's the basic idea of implicit differentiation. Now it's just a matter of some more practice probably as we go along and be able to do it. But, you know, somebody was saying, well, how do you know you shouldn't do explicit? How do you know you shouldn't get the y by itself? Well, rarely do you. It should be pretty easy. If I looked at an equation and could immediately say, oh yeah, here, I'll just boom, 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 and I'll have the y by itself, then you might do that, right? If you had x squared plus y squared equals 1, yeah, it's pretty easy to get the y by itself, and then do your derivative, so that'd be fine. But one like this, you couldn't get the y by itself, because you'd have squareds, and there's just no way. So you just don't even try. Just go right into implicit differentiation. Same with this one. You can't get the y by itself. Right? You could move this x squared over here and factor out a y, but then you'd still have a y left there. There's just no way to get the y by itself on that problem, number 9. Right? So you have no choice. All right, anything else about this implicit differentiation?
So there will be stuff like this on it.
Gateway will have some like this. This one's probably too extreme, but this one could be on it. Right? And you'll be able to tell. I mean, and there won't be more than 1 or 2 of them. So 8 of them are going to be y equals some x's, and you do the derivative, right? And 1, maybe 2, will look like this. And you'll know those are ones you should do implicit differentiation, right? I won't give you any that are like in between. I'm not going to give you x squared plus y squared equals 1, where you could maybe do implicit or maybe do, get the y by itself. I'm either going to give them to you with y by itself, or I'm going to give them to you like this, where you just do implicit. Okay? All right, let's get your notes out then, and let's go into the last kind of new stuff we need to do in this chapter, because we have the rule that involves inverse trig functions that we need to get to. And I want to do more than just give you the rule, okay? Now, for the gateway test, that's all you need, okay, is the rule, and do the derivative. That's all you need. But for this class, you need more than that when it comes to inverse functions and inverse trig functions. We need to understand some more stuff. So we're going to talk about some of that today. Try to review some things from last year. And some of this is going to hopefully look familiar. But I don't know. All right, so here's where we're going to start. We're going to start by just talking about inverse functions. Excuse me if the writing is kind of choppy, but my regular tablet's not working, and I'm not very happy with it. So I got to use this one, and this doesn't seem to work very well. All right. Now tell me, when you hear the word inverse, well, just the word inverse, what do you think of? I think I already told you some of my pet peeves about this earlier in the year, but opposite, negative, reciprocal. Those are the common ones, right? And you're not far off. Because and this is my pet peeve, and it's partly our fault when we teach it, and we don't probably teach enough of it. There are a lot of different inverses. Okay, like if I gave you 2/3, if I gave you this question, what's the inverse of 2/3? What would come to mind? 3/2. I heard some people say negative 3/2. What about negative 2/3? Well, two of those three would be inverses, right? 3/2 is an inverse. Now, to be honest, if I ever ask you that question on a quiz, you should just refuse to answer it and just say, that's a terrible question, right?
First question on the evening test.
Because it is, right? You'd be right. What's the inverse of 2/3? What do you mean? What kind of inverse? The multiplicative inverse is 3/2. I just like saying that, actually. Multiplicative inverse is 3/2. That's the reciprocal. The additive inverse is the opposite, negative 2/3. So there's additive inverses and there's multiplicative inverses. Now, if you do the reciprocal and the opposite, that's a whole other thing. I think that's when two lines are perpendicular or something, right? They have opposite reciprocal slopes, that kind of thing. So that'd be like two inverses, I guess. But these are inverses. This is the multiplicative inverse, this is the additive inverse, and neither one of those are what we're talking about here. We're talking about inverse functions, okay? So let's kind of forget those for a second. Now, the one we're going to want to talk about here in a little bit is inverse sine. Now, this is where, another reason it's my pet peeve of mine, I guess, is why we use this notation for inverse. I have no idea. But this has been used for a long time as inverse. Well, people think that means reciprocal, because it usually does, right? Negative 1 power usually means reciprocal. Well, what's the reciprocal of sine? Cosecant. Well, that's not what this means. This doesn't mean cosecant. This means arc sine, right? That's the phrase I'm going to use for the inverse function of sine is arc sine. Because I want to get away from this negative 1 notation. On your calculator, though, it uses the inverse sign. It uses that negative 1 to mean inverse. So when we're talking about the inverse of the f function, we use this notation right here, this negative 1. It means inverse of the function. It does not mean reciprocal, okay, at all. So don't, okay. We'll talk about some reciprocals. There's reciprocals involved in some of this stuff that we're doing, but it doesn't have anything to do with function inverse. All right, so now tell me what you remember about function inverses. Anything at all? Not this stuff. Yeah, not this. Anybody remember anything about function inverses? How about this? There you go. Say that louder. Interchange the x and y values. That's right. Does that sound familiar? Let's say instead of x and y, let's say input and output. You interchange the input and output. Okay, so one thing we know about inverse functions is we interchange the input and output. Now we're going to look at some examples. Now it's going to get kind of, I'm going to throw a lot of stuff at you here and hopefully tie a lot of it together. You interchange the input and the output. That is true. Okay, how about graphically? It's a flip in the line y equals x. It's a more specifically a reflection. This looks like a third grader. A reflection in the line y equals x. All right? So, let's look at an example. Let's do y equals x squared. All right? We know the graph of that is just a parabola. And that is a function. So I could write that f of x equals x squared, but it'll be easier if we do y. Now, let's do the inverse of that. So let's interchange the x and the y, the input and the output. right? And we get that. And then what was your next step? Interchange the x and the y and then solve for y. So let's go ahead and solve for y. Well, we would do the square root of both sides, and whenever you do the square root of both sides, you got to remember to do plus or minus square root of x. Now, unfortunately, though, that is not a function, right? If you were to graph this, it would be this, right? Now, if I would draw that over here on this, you could kind of see that this is a reflection in this 45-degree line that I could draw right through here, right? If you were to draw this line, you could see that this parabola is a flip or a mirror image, right, in that line y equals x, because that interchanges the x's and the y's. Now, that's not a function. Now, let's think about this a minute. What is it that causes, what about the original function caused my new function to fail the vertical line test? Yeah, but I mean, you remember, it is the plus or minus, but do you remember hearing about the horizontal line test? When it comes to inverse functions, there's something called the horizontal line test. If a function fails the horizontal line test, look at the black one here. When you reflect it, what's going to happen? It'll fail the vertical line test, right? Because when you interchange those x's and y's, a horizontal line is y equals, a vertical line is x equals. So when you interchange the x and the y, a horizontal line becomes a vertical line. So if I was to give you a function and say, is this function invertible, means does it have an inverse function? To have an inverse function, it has to pass the horizontal line test. If it doesn't pass the horizontal line test, it won't pass the vertical line test when you do its inverse. So how do we do that? How do we make a function invertible? Well, we have to restrict its domain. So what we would have to do here is we would have to take, and I'll do this in blue, we would have to only take, oh, that was bad. We would have to only take part of it so that it would pass the horizontal line test. And we would not do this part of it. We would only do this part over here. That way, when we flip it, we would only get this part here. And we would not get this part down here. Okay? And so what we would say here is that we only want x to be positive. That way over here, our y's would only be positive, right? Again, there's that idea of interchanging the x and the y, interchanging the input and the output. That way we would only get one output for every input. It would pass the vertical line test. So sometimes when we do an inverse, we have to restrict the domain to make that happen. Let me show you what this looks like. You're going to have some of this on some of your homework questions. So, if I was to take 4 squared and then do the square root, what does that equal? 4, right? Now that might lead you to believe that if I do x squared and then do the square root, that I get what? X, right? Now that makes sense. And inverse functions are kind of like opposites. Then what that should mean is they should undo each other. They should cancel each other out. So x squared square root should equal x. Unfortunately, as we just saw, that only works if x is positive, right? That's what we just showed on this last page. We have to restrict the x to be positive, because if I was to do this, if I was to start with a negative 4, do I get negative 4 as my answer? No. Negative 4 squared is 16. The square root of 16 is positive 4, not negative 4. So, in reality, when I do the square root of x squared, what should this answer really be over here? Not plus or minus. You never get a minus. It's what? Absolute value of x. Matter of fact, try it on your calculator. I want to do something else on calculators later, so go ahead and get your calculators out. Type in square root of x squared on your calculator. Do you get square root of x? Okay. All right. So those seem like they should be, it should just cancel itself out, but it doesn't. All right. Now, let's look at another function that is an inverse function. Let's look at e to the x. Okay? Y equals e to the x. Now that graph is just a, something like that. Now does that pass the horizontal line test? So when we invert this, it should pass the vertical line test, right? Now you guys all know, don't you, what's the inverse of e to the x? Natural log of x, right? But let's watch it happen here. So let's interchange the x and the y. So we get x equals e to the y, right? Now how would we solve this for y? Natural log of both sides. So if we do natural log of e to the y, what's natural log of e to the y? That's just y. And sure enough, we get y equals ln x. The graph of y equals ln x is this graph right here. Now maybe this will help you remember the ln x graph. Let me put it in red over here. It is this right here. Sure enough, it is a reflection in that line right there. And there's no problem with, we don't have to restrict the domain or anything. So in this one, we literally can do ln e to the x is x, or ln e to the x is x, or e raised to the ln x would be just x. We don't have any bars, we don't have to worry about any restrictions in the domain. Okay? All right, so that's a little bit about inverse functions and those kind of things. All right, now let's talk about sine, because that's the one we really want to get to today. So let's talk about y equals sine x. The graph of sine x does that pass the horizontal line test? No. Right? So what we need to do is restrict it so that it does. Now we have a lot of choices of where we could restrict it. The one that we often, and your calculators and most books will do, is right here. If we restrict it from here to here. Now the reason that's a good idea is it gives us all the possible sine values from -1 to 1. It hits them all. But it doesn't repeat any. All right? And so this little piece here passes the vertical line test, or the horizontal line test. Now, what would the inverse look like? Well, the inverse, we would interchange x equals sine y. Right? Now we got to solve for y. How do you solve for y? What do you do to both sides to get rid of sine? From last year. You don't do it very often, to be honest with you. It's inverse sine, or arc sine. So what you would get here is y equals arc sine of x. Okay? And that's the inverse function of sine, is arc sine. But it's a function. Means it only has one output. Now let's think about this a minute. This right here, these are angles, right? Like pi halves, pi thirds, that kind of stuff. And then these are values that go from -1 to 1. So that's the same thing is true here. These are values that go from -1 to 1, and these are angles right here. We interchange the inputs and outputs. So in this problem, in arc sine, these are values that go in there. These are -1 to 1 values, and these out here are angles. So the output of sine, arc sine, is angles. Right? Now, when you do a trig problem, you don't have, well, you can write this down if you want. When we do a trig equation, we usually get to this point, and we stop. Right? When we're solving a trig equation, we usually get to here. And then we just say to ourselves, okay, what angles give me a sine of root 3 over 2? What is it? Pi thirds, but also 2 pi over thirds. Now wait a minute. If we get two answers for our inputs here, on the inverse function, you would have two outputs. Can you have two outputs? You can't have two outputs, can you? Right? And that's always an issue, right? We always talk about, well, it'd be pi thirds plus 2 pi n, and 2 pi thirds plus 2 pi n. You have all those different possible inputs for this problem. But if we're going to talk about the inverse function, we can only have one output, right? So if I want to get x by itself, I never make you do this step, and I'm not sure that your teacher last year ever made you do this step, because they're really two different things. Okay? It's kind of like doing the plus minus with the square root. If you stop right here and you think to yourself, what are all the values that make this happen to get this? But what I do is I do the arc sine of both sides. Now type that into your calculator. Do arc sine of root 3 over 2. Now to get arc sine, you go to the trig button. You go to the trig button and do the sine inverse, sine minus 1. And then put root 3 over 2. And tell me what you get. Do you get pi thirds and 2 pi thirds? Do you get pi thirds plus 2 pi n? Do you get all that business? You just get pi thirds, don't you? Why is that? Because your calculator is restricting it. Look up here on this graph. Your calculator is restricting it to just from here to here, which is negative pi halves to pi halves, which would be what quadrants on the unit circle? First and fourth, right? Negative pi halves is down in the fourth quadrant, and pi halves is up in the first quadrant, right? So you'd have pi halves to negative pi halves, that'd be the first and the fourth. First quadrant gives you the positive values, fourth quadrant gives you the negative sign values. So, for this one, it gives you the first quadrant values. So just don't type in your calculator yet, but what if this was negative? It should give you the fourth quadrant value. What's the fourth quadrant value? Well, you might think 5 pi thirds, but that's how we normally do it in the unit circle. But right, normally in the unit, so if this was negative, okay, this is interesting. If this was negative, the way we usually do it is from 0 to 2 pi, don't we? So that would be down here, and normally we would call that 5 pi thirds. But is that between negative pi halves and pi halves? No. So type that in your calculator now. Go ahead and put the negative on there. What's it give you? It gives it to you as negative pi thirds. Because again, our restriction is from negative pi halves to pi halves. So that's what the calculator is programmed to give, and it's programmed to give this as a function. So it only gives out one value, even though there's a lot of other places where the sign is negative root 3 over 2. It's programmed as this function to only give you the one output. Okay. Now, there'll be some issues that'll come up on your homework. Well, what the heck? I tell you what, that's probably let's just do that right now. While we're doing this, then we'll get into the derivative stuff. So here's some problems that you used to do in trig last year. One would have been something like this: arc sine of root 3 over 2, which is what we just did. And we all said that was pi thirds. Okay? Good enough, because that's in that quadrant. All right, then you probably did something like this: arc cosine, write this one down, of 3/5. Now that, unfortunately, is not an angle you know how to do. So the directions would have been not find this, but maybe draw a picture that represents this. Draw a picture that represents the angle whose cosine is 3/5. So you remember doing this? This is where SOHCAHTOA comes in. What kind of a picture would have a cosine value of 3/5? 3. hypotenuse 5, which of course, Pythagorean theorem, we know that would be 4, but we could do 25 minus 9 is 16 square root, right? So this would really be the square root of 5 squared minus 3 squared, right? And that's where that 4 comes from, right? And so the problem you usually were asked was this. What's the sine of the arc cosine of 3/5? Does that look familiar at all? Okay. What's the sine of the arc cosine of 3/5? And your answer to that would be 4/5. So what you would do is you would draw the picture that what angle is created so that the cosine is 3/5. It would be this. Fill in the rest of the triangle, and then what's the sine of that? 4/5. Or what's the tangent of that? 4/3, right? Opposite over adjacent, that kind of stuff. You'd get those kind of questions. All right, so now, one of the things you'll have on your homework will be questions like this. What's the tangent of the arc sine of, let's not make it too tough, let's say 3x. What's the tangent of the arc sine of 3x? Oh, by the way, type that in your calculator. Let's see if it does that. Let's see what you get here. Sine of the arc cosine of 3/5. See if it gives you 4/5. Gives you 4/5. Okay. But I want you to be able to do this as a triangle. But again, you could type some of this into your calculator to see, but some of this is going to be on the homework. Not on the gateway test, right? We haven't gotten to the gateway test part of this. And I understand you're mostly thinking about that. I understand. And you're going to have plenty of time to be focusing on that. But we want to get through some of this. All right, so what would we do here? Well, same thing. We would draw ourselves a picture. Okay? And I'll keep these positive for right now so we can keep them in the first quadrant. But if this was a negative 3/5, then you'd say, well, where's cosine negative? Well, first quadrant positive, this quadrant negative. Maybe, well, I'll show you that in a second. We talked about sine is limited from negative pi halves to pi halves. What about cosine? What about tangent? What about those? No, I'll show you those in a second, but I'll keep them positive for right now. So arc sine of 3x. What kind of picture would have the sine equal to 3x? Put 3x there. Hypotenuse 1. Wouldn't that work? Right? That would have a sine of 3x, opposite over hypotenuse. So then what would this leg be? Square root of, because it would be 1 squared plus 3x squared, which would be that, right? Equals, oh wait, no, that's not right. Equals would go there. This would be plus. And then whatever we're looking for there, German shorthand, right? This would be the German shorthand. So what do we need? We need 1 minus 9x squared and then the square root of that. All right, so wouldn't that be that leg right there? Okay. So now we want the tangent of that. So what's the tangent of that? 3x over root 1 minus 9x squared. I'm curious. See what I've never put this in the calculator. Put it in the calculator. You do it? Is that what you do? That's pretty cool. So you do tangent of arc sine of 3x, and it gives you that right there. Now, if you remember what our rule was yesterday, some of you might have written it down. You might start to see, all of a sudden start seeing some things here that look similar to what that rule was for arc sine when we did derivative. You start to see some of that a little bit. And we're gonna put this all together where this comes from. But this is just some stuff from trade class last year, really, with these different ideas with sine and arc sine and so forth. All right, so now let's get into the idea of the derivative. Now, first, I just want to show you a quick, okay, so there was a picture of that. We'll come back to that one. So here's the sine function. So here's this idea of restricting sine from negative pi halves to pi halves. Okay, and then this would be the inverse sine over here, okay, in the black, or in the blue, I mean. All right, that'd just be its reflection. And notice what happens. Notice how it interchanges. The blue graph, the inputs go from negative 1 to 1, and the outputs go from negative pi halves to pi halves, because we're interchanging the inputs and outputs. Okay, cosine we restrict to the first and second quadrants. Cosine we just restrict from 0 to pi. Positive in the first quadrant, negative in the second quadrant. So the arc cosine would be the blue graph. Again, the outputs would go from 0 to pi. The inputs go from -1 to 1. And then tangent, you remember the tangent graph has all these branches. Well, one branch would be we call it 1 to 1 or invertible. One branch would pass the horizontal line test. So we just take one branch, which would be negative pi halves to pi half. So again, that'd be first and fourth quadrant. Tangent's positive in the first quadrant, negative in the fourth quadrant. And then there its inverse would be in blue there. And we'll just stick with those three as far as what we'll worry about. Okay, so those are just that's just kind of some informational things about sine and cosine. All right, now let's get to derivatives. Now let's take all that information about inverse functions, and now let's talk about how this relates to derivative. Of course, derivative is slope. Now, if you take two functions that are inverses, so these two blue pieces of a function are inverses. They're not sine or cosine or anything. They're just functions. But do you notice how they're reflections? Here's our y equals x. So, right, they're mirror image. Let's talk about slope a minute. The rise on this one. What do you notice? It's bigger than that, isn't it? Would this rise be the same as that right there? Well, let's think about it. The rise is the y, and the run is the x. If we're interchanging the y's and the x's, isn't that just interchanging the rise and the run? Shouldn't it be? So the rise over the run on this one is the run over the rise, or reciprocal, right? It would seem like with inverse functions, if all you're doing is interchanging the x and the y values, then that ought to be the reciprocal as far as slope. Not negative reciprocal, but reciprocal. Matter of fact, look at both of these are positive slopes, aren't they? It looks like they should be reciprocal. Now, there's another catch to it. They're not at the same location. The slope on this one, that's the reciprocal of the slope on this one. This one happens at the x-coordinate b. This one happens at the x-coordinate a, which was the y-coordinate of that one. But that makes sense because we're interchanging the inputs and the outputs. So what's happening is not only are they reciprocal slopes because of rise and run, but the one slope on the one function happens at the input and the other slope happens at the output of the other one. They're interchanged. That might be worth writing down. I'm not sure there's a good way to write it in a way that makes a lot of sense, but I think we should say it. So,
let's write it down anyway.
Let's write it down anyway. Inverse function. Now again, this is something that is going to be useful much later on in the class, not so much as we do this gateway test. Useful in your homework today, and then hopefully something we can come back to and remember later on. But so inverse function slopes are reciprocals of one another at, actually I don't want to make it second bold. Inverse function slopes are reciprocals of one another. How can we say that? At the input of one function and the output of the other. I don't know. Let's do an example and see if that makes sense. Okay? Reciprocals of one another at the input of one function and the output of the other. So, our example will be this. Let's go back to the y equals x squared. And let's use the point 3 comma 9. Right? That would be a point that would be on this function. Now let's do the derivative of it. So y prime would equal 2x. So y prime at 3 would equal what? 2 times 3, which is 6, right? So, and that kind of makes sense. If we look at the y equals x squared, which would be a parabola, we go up here at the point 3,9, right? We would have a pretty steep slope. We'd have a slope of 6. That seems to make sense. All right, now let's do its inverse. What did we say the inverse function was? Square root of x, which would have the point 9,3, right? Interchange the x and the y. Of course, we know we're about to do a derivative, so let's write that as x to the 1/2. So the derivative of that is 1/2 x, which might be nice to rearrange a little bit. Let's take that negative 1/2, take it down to the bottom, and that'd be square root. So it'd be 1/2 square root of x. Wouldn't that be also a way to write that? Now, what would be, see if you're following this at all. Cross my fingers. What would be the slope of interest here at what point? Y prime of the input of 1 would be the well, it's actually the output of, it's the input of the other. It's the input of this is the output of this, right? The input of this is the output of that. That's kind of what I was trying to get at there. What's the y prime of 9? You put a 9 in here, you'd have square root of 9 is 3. 2 times 3, 1/6. Now, think about the square root graph would look like this. Think about out here at the point 9,3, right? Have a slope of about 1/6. So that looks somewhat like the picture that I just showed you that was from the book, okay? Now, where you run into these problems on the AP tests and so forth is exactly what some of you were saying. You want to put a 3 in here and you don't, okay? You get this idea that they're reciprocal slopes, but one of them happens at 3, the other one happens at 9, which is the output of this one, is the input of that one because of that interchanging idea, okay? Now, let me show you how this applies now to derivative rules, okay? Your book calls this Theorem 5. Yeah, none of this has to do with it. Here's Theorem 5. It says this. We start with the fact that f and g are inverses. Start with the fact that f and g are inverses. Okay? So that means if f and g are inverses, then what should f of g of x equal? What should f of g of x equal if these are inverses? Think of square root of x squared. Think of e to the ln x. They should just equal x. Now, I know square root of x squared was absolute value of x. That's just a domain issue. So we're going to ignore just domain issues right now. We'll assume that we have limited our domain so that we can deal with this. So right now we'll just do this, okay? So f of g of x should just equal x if f and g are inverses. They should cancel each other out. Let's do the derivative of both sides, like an implicit differentiation kind of. Do the derivative of both sides with respect to x. Well, here we do a chain rule. So this would be f prime of g of x times g prime of x. And the derivative of x is 1. Now let's divide that whole f prime mess over there. This is saying what we tried to write in words this is saying it in math symbols. This is saying that the g derivative is the reciprocal of the f derivative, except at the output of g. So this is the g slope at x, and this is the f prime slope at the output of g, right? So the input of one, the output of the other, and they're reciprocals. So that is saying it in math symbols what we were trying to say in words before, and what our example was just showing there with the 6 and the 1/6. And it really just comes from this idea of the chain rule. Okay, finally, the grand finale. I know, it seems like we're all over the place. Let's do this with arc sine. So our goal here, our goal today has been to get this. Derivative of arc sine of x. That's what we're trying to get. Right? And we're trying to get a rule for that. Okay? That's what we want. So here's what we're going to do, and you're going to see how it ends up being kind of another form of that theorem 5 that we just wrote down. So we're going to start with this problem right here. We're going to say that sine of arc sine of x is equal to x, right? Because that would be true. That would be true. Arc sine of x. So that pretend, for example, we put root 3 over 2 in here, right? What's root 3 over 2? What's the, I'm sorry, arc sine of root 3 over 2? We said a little bit ago. Pi thirds, right? And what's the sine of pi thirds? Root 3 over 2, right? And we don't have any domain issues. Now, on your homework, there's going to be a problem where if you switch sine and arc sine, there is a domain issue. Now, if you remember that, when we did x squared and then the square root, we said we had a domain issue there we had to deal with. There's not a domain issue if you do it this way. There's not a domain issue if you do it in this order. Because think about it. Can x be negative inside the square root? X can't be negative inside the square root. So when you do square root of x and then square it, you're going to get x every time. Because x has to be positive in that case. So you don't have to, you have no domain issues when you do it in this order. When you do it in this order, you have domain issues. So when we do this in this order, we have no domain issues, right? Arc sine of 1/2 is pi 6. Sine of pi 6, 1/2. If we would have flipped those around and done them the other order, then we would have some domain issues, okay? Well, you guys are looking at me like I'm crazy. Why would we have domain issues, you say? All right, let me do an example. Let's do 7 pi thirds. Okay? What's the sine of 7 pi thirds? Now wait a minute. If there were no domain issues, what should arc sine of 7 pi thirds be? Should be 7 pi thirds, right? What is sine of 7 pi thirds? 7 pi thirds, that'd be 6 pi thirds, which is 2 pi, and then another pi thirds. So what's sine of 7 pi thirds? Root 3 over 2. What's the arc sine of root 3 over 2? Pi thirds, right? Because we stick between negative pi halves and pi halves. So if this angle in here is not between negative pi halves and pi halves, you're not going to get the same thing out. There are domain issues if you do it in that order. There's a homework problem you have. There's a homework problem you have. I'm losing it. So exciting. I just can't concentrate. Okay. That was. All right. So depending on. Yeah, they have no idea. They have no idea what just happened. All right, it's probably better. Okay. So anyway, no domain issues. So we get this. So now, remember what we did? Right? What? Right here, we did the derivative of both sides. So let's do that here. Let's do the derivative of both sides. So we're almost there. So the derivative of the outside is cosine. We leave the inside alone. Times, the derivative of arc sine. That's what we're trying to find. Okay, well, let's just write that. Let's just do derivative of arc sine. That would be this. We don't know what the derivative of arc sine is, so we'll just write derivative of arc sine, right? Because that's what it would be. Derivative of the outside, leave the inside alone, times the derivative of arc sine, which is what we're trying to figure out. And that equals 1. Oh, so now could I just take this and divide it over? Right? So on this side, we just have derivative of arc sine, which is what we're trying to figure out. So derivative of arc sine would equal 1 over cosine of arc sine of x. Wait a minute, this looks like something from trig. This looks like something from like 12 slides ago. This looks like that, doesn't it? Where we did tangent of arc sine of 3x and we drew a picture. Okay, so let's do that. So let's do, so this bottom piece, so this bottom thing, I should be able to draw a picture. What kind of a triangle would have arc sine of x? Where would the sine equal x? Opposite over hypotenuse. So this down here would be what with Pythagorean theorem? 1 minus x squared and the square root. And so now come back to this, come back to my fraction. So this triangle would be this inside, arc sine x, and now I want the cosine of that. So adjacent over hypotenuse. So this bottom is just root 1 minus x squared. Right? It would be that over 1, which is just that radical. And that's the whole bottom, is just that. And sure enough, there's our derivative rule. A lot of stuff. But a lot of review. I mean, you know, a lot of good review of some trig things, some things that we need to know about inverse functions and this whole interchanging of x and y. But in the end, it resulted with this derivative rule. Now, when we do it, we want to not think of x there, but u, right? Because we're normally going to have arc sine of some stuff. So we'll put that as a u. So we'll go ahead and grab our derivative rules from yesterday, and we'll put those up again. And there then are the 3 rules for the inverse trig functions. All right, so we have a u inside, and that u is what goes down there. That's the part where we say we keep the inside the same. Good luck. And so this part here is where we say we keep the inside the same. Like, so we say, okay, we do the derivative of the outside, which is all this square root business. Keep the inside the same means the u just goes down there. And then derivative of the inside is the u prime. Notice our cosine is the same thing except a negative on top. And that reason is, think about how we did this. When we did the derivative of sine was cosine. Well, if you do the cosine, the derivative is negative sine. So that's why it ends up being a negative, but the rest of it works out the same. But then our tangent, notice there's no square root. Okay, so be careful when you write that. There's no square root, and it's a plus down there. All right, so your homework is the 3.4, and then keep practicing on page 195. Now, if you had some questions on 195, we'll take some of those tomorrow, or obviously you can come in before school and that kind of thing as well. But on the 3.4, you'll get into some things where they use arc sine. Now, keep in mind, listen, arc sine now is just like any other function. You could have stuff inside of arc sine, right? So that would be the u. That would be your, your, good luck. That would be your u. That'd be your inside. But you also could have arc sine as an inside function, right? Like you could have something like this. And again, the rule is derivative of the outside. So ln of something is 1 over that something times the derivative of the inside. And then you tack on the derivative of arc sine. right? So you can see it in a variety of ways as you do it. All right, when you're doing your problem. Okay, so go ahead. You have the rest of the time to do your work. Yes.
If you had like the arc side times the x squared plus 3, like